If you've ever dreamed of upgrading your own 3D designs to real metal, it is surprisingly affordable. But metal does not forgive. See, my dad's lab repair firm has spent decades saving critical medical equipment from the landfill. This test tube centrifuge, for example, is practically indestructible except for one injection molded rotor, which is a maintenance part, needing replacement when cracked due to constant wear and tear. A replacement used to cost over $600, but not anymore. They are extinct. Can a bit of CAD experience and desktop 3D printers like our Sovol Zero or Bamboo Lab H2S save this machine from the scrap heap? We started by recreating the part in plastic, but then we asked the ultimate maker question: what if we took this successful FDM design and upgraded it to solid metal? Thanks to our sponsor JustWay, we bypassed layered plastic entirely and manufactured the replacement out of industrial-grade aluminum. Stick around to see the crucial design mistakes we made so you don't have to. See whether it survives the 2800 RPM spin test and a neat trick using our MOPA fiber laser to automatically serialize parts in Lightburn along the way. I'm gerGO and welcome to gerGO Print 3D, the YouTube channel where we explore 3D printers, laser cutters, and occasionally try to spin metal parts at terrifying speeds. If you're new here, we love taking on practical DIY repair projects, and as always, this video includes curated, translation-ready subtitles, detailed chapter markers, and multiple audio tracks to give everyone the absolute best experience. Let's get to work. Our patient today is this trusty 20-year-old lab centrifuge. The main swing-out rotor disc literally cracked under the pressure, becoming the fatal weak link. So we broke out the digital calipers and got to work in our CAD program. I quickly dismissed the idea of 3D scanning this part. The geometry is actually pretty straightforward, and doing it manually ensures our dimensional accuracy is spot on. After a few hours of measuring, drawing, and tweaking, we had a solid two-piece design ready for testing. For our very first draft, we just wanted to test the physical fit. We sent the bottom half to our lightning-fast FS on S1 Pro in blue PLA, and the top half to the little Sovol Zero in orange PLA. I know, blue and orange. We accidentally made a spinning rotor that looks exactly like an identity disk battle straight out of Tron. We've got the blue side fighting for the users and the orange side working for the CLU. And hey, if you fight for the users, throw your disk at the like button please and hit subscribe so you don't get de-res from our grid. Thank you if you did, it really helps the channel out. The two halves fit together beautifully after we removed the supports, but then came the moment of truth at the centrifuge. We tried to drop it onto the spindle and no, it wouldn't budge. The bore hole was just a fraction of a millimeter too tight for the metal shaft. But hey, you know our motto, we make mistakes so you don't have to. Shrinkage is a real thing in 3D printing, especially on inner diameter holes. While we were back at the drawing board fixing the tolerances, we did a quick weight check. The original solid piece came in at 88 grams, while our hollowed out PLA prototype was only 52 grams. Less weight means less strain on the motor, which is great. But PLA is brittle, and in a lab environment where things need to be wiped down with harsh chemicals, it would degrade incredibly fast. It was time to level up our materials, design the swing out arms, and break out the heavy-duty plastics. Strap in. We are only at level 2 and already upgrading to ABS. Back in FreeCAD, we widened that central bore hole by a fraction of a millimeter to give us the needed clearance. While we were at it, we went ahead and designed the swing out arms and the little plastic retention springs that hold the test tubes in place. Then we sent the updated files to our Bamboo Lab H2S to print everything out of ABS. ABS is fantastic for thermal and chemical resistance, But as we always say, safety first. We made sure our inline fan was venting those toxic fumes straight out the window during the entire print. If we need something bigger, our SV08 Max can also handle ABS now. After removing the supports, we had a fully functional, highly durable plastic rotor. But remember that light burn trick from the beginning I mentioned? We took these white ABS parts over to our Monport GPro 60 MOPA fiber laser. I used Lightburn's serial number feature for the very first time in my life to automatically increment and mark numbers 1 through 12 around the slots. You just put DD in place of the numbers and select serial number in the drop-down list. What threw me off was that the numbers did not appear until I realized the placeholders only get replaced during the engraving process or when you hit preview. The markings on the white ABS turned out a little bit foggy, but they are completely legible. This will come in handy to mark the final aluminum piece as well, only changing the laser power. We also did another weight check. The original part with 4 test tube arms weighed 122 grams. Our ABS version, just 83 grams. With bated breath, we took the new ABS assembly to the centrifuge. Does it fit? It slid onto the axle perfectly. We plugged in the machine, pressed start, and it spun flawlessly. We even tested it with the lid open, just to make sure the swing out arms were deploying correctly. The ABS part works perfectly, and honestly, we could have just stopped there. But where's the fun in that? While the ABS rotor is a massive success, a lab setting means these parts are subjected to harsh disinfectants, sometimes even boiling water and constant daily stress. To guarantee this machine runs for another 20 years, we needed metal. And that is where our sponsor, JustWay, comes in. You don't need to own a multi-million-dollar metal 3D printer to get industrial-grade parts. We simply uploaded the same STL models to their website, selected SLM, selective laser melting, in aluminum, and got an instant quote. Are you ready for this? The cost to 3D print these 2 custom solid metal pieces was just $122. Compare that to the $600 the original manufacturer used to charge for a piece of injection molded plastic. Start thinking about using this technology for your own projects. With our coupon code JustWay at gerGO Print3D-10, you can save an extra $10 on orders over $30, excluding shipping. But be quick, this code can only be redeemed by a limited number of fans. See the terms in the description below. When the JustWay box arrived, it was like a holiday in the workshop. Do you hear those Christmas bells? The pieces fit together flawlessly right out of the packaging, and there is just nothing quite like that satisfying clinging sound of real solid metal. The surface finish and workmanship are absolutely premium. But as we quickly found out, swapping from plastic to metal introduces a whole new set of challenges, which we are happy to deal with so you don't have to. First, we needed to cut M3 threads into the aluminum to screw the 2 halves together. Yes, I could have ordered a part with these threads, but we got a thread cutter from AliExpress earlier, very usable under 20 bucks. Chugged it into our Hot 16-volt drill and carefully tapped the holes. Metal shavings went everywhere, so we quickly cleaned up the mess using our Hot AutoCare mini vacuum and then assembled the halves using our Hot Pixel Drive screwdriver. I guess you can see a pattern here. Use our code gerGO at hottools.com to get any of these for 15% less. We proudly carried our gleaming metal rotor to the centrifuge. We dropped it onto the spindle. The bore fit perfectly. Whew. But it wouldn't lock in. The keyway slots for the drive pin were too narrow. See, plastic has a tiny bit of flex, allowing it to squeeze past tight tolerances. Aluminum, zero flex. If it's off by 1/10 of a millimeter, it is not getting on. Out came the Hotto Precision Rotary Tool. We carefully widened the keyway slots, making a tiny pile of aluminum dust in the process. After a quick test fit, boom, it locked into place. But we weren't out of the woods yet. When we tried to attach the swing-out tube carriers, their pivot pins didn't fit into the trunnion sockets either. The tolerances were just too tight here as well. I started filing them down with the rotary tool, but getting a bit impatient, I actually switched to my power drill to open them up faster. Now, a very serious warning if you ever do this. You have to make absolutely sure you sand both sockets evenly. If a bucket sits at a slight angle, you will create an unbalanced load, and at 2800 RPM, an unbalanced load will tear a centrifuge apart. But learning from our mistake, you won't run into anything like this. Your slots will be the right size. With all 24 sockets filed and the swing-out buckets attached, we assembled the two halves one last time. Spinning it by hand felt incredibly smooth, but there was one lingering worry: the weight. The total aluminum assembly weighs 316 grams. That is about double the weight of our ABS version, which came in at 163 grams, and still somewhat heavier than the original injection molded part. Would the old motor handle the extra mass? To find out, we placed a light reflecting sticker on the motor shaft so we could use a digital rotometer. By pointing the rotometer through the small monitoring window on the lid, we can measure the exact speed. We fired it up with the ABS rotor first as a baseline. The rotometer clocked it at a blistering 2831 RPM. We swapped in the solid aluminum rotor, closed the lid, and cranked the dial. It was a little loud as it spooled up, but it stabilized beautifully. We pointed the laser through the window, 2801 RPM. The motor didn't even break a sweat. It lost a negligible 30 RPM, successfully spinning a massive chunk of custom printed metal. Test cleared. One final round under the Monport GPro 60 MOPA fiber, this time tuned for aluminum. The marks look sharp and permanent. Email us for our laser material libraries. This project was a total success. The lab now has a perfectly functioning ABS rotor and an infinitely durable aluminum version they can boil, disinfect, and use for decades to come. They can decide which one they want to use in the long run. The biggest takeaway for us: the next time we design a part for SLM metal printing, we will add significantly more clearances to the design to account for that lack of flexibility. We could also easily hollow out the design much more to reduce the weight, because solid aluminum is so incredibly strong that even with half the material it would easily hold up to the forces of the centrifuge. Yes, the turnaround time for outsourcing metal parts isn't that magical overnight satisfaction we get from our desktop 3D printers, but saving a piece of lab equipment from the scrap heap with a part that is better than the factory original, that is what this hobby is all about. Just remember to use our discount code when you order your metal parts from JustWay. And if you're wondering about this 3D printing themed mechanical gaming keyboard from Melgeek, it is soon going to Levy, but not before we tell you how we 3D printed various back plates and even had to design and replace one of the side panels because of a stupid mistake. Yeah, we keep making those. Turn on notifications so you can be the first to watch that video when it comes out. If you want to see another crazy repair job, fixing our bamboo lab that kept blowing the fuse, click here and start designing your own replacement parts in FreeCAD or Fusion watching this. Now go print 3D. Thank you for watching another gerGO Print 3D video all the way to its end. Keep spinning and stay safe.